Hi, so in this video I'm going to go through some force problems involving strings and ropes, and just kind of show you how we can work with those, how we can approach some of these different problems. The interesting thing that using these strings and ropes introduces into force problems is that they're a way for multiple objects to interact with each other, and so objects to exert forces onto each other. So let's start with a really simple example. So we've got a pulley, which is basically just a sorry, that's a bit bright. Hopefully that's a bit better. Which is basically just a wheel that's free to rotate, and it's being held somehow, and suspended from it there are two blocks. I'm going to call them mass 1 and mass 2, and they're suspended like this, and we're going to say that that this is the heavier one. We're going to say that M2 is bigger than M1. Okay, so they're connected by a single string that goes over this pulley. The pulley's free to rotate either way. There's no friction, and this is all oriented so gravity is down here. So how does the question is, like, what is the acceleration? What is the acceleration of this like of this system? I'm going to try and, is that better? That's a little bit better, I suppose. There we go. Okay, so let's leave it like that. So how do you accelerate? So the first thing, as with all the force problems, is to draw free body diagrams. So these are two objects, they're two separate objects, and the idea of the F equals ma equation is that it applies equally to every single object, and so we can basically draw two free body diagrams here, one for each of the masses. So M1's free body diagram would look like this. It would have tension in the rope pointing up, and it would have its own weight pointing down, M1G. And then in this direction, for the other mass, we would have M2. It would have tension pointing up, and it would have its own weight pointing down. Okay, so notice that I have not called these T1 or T2. And the reason I've done that is because we're going to assume this is a light string. And for a light string that's that's free to rotate like this around a pulley, the tension all the way along the rope is constant, or along the string is constant. So this tension is the way in which these two objects interact with each other. They exert tension on the string, or they exert a force on the string, and that comes out as tension in the string, which is then exerted on both of them. So we could write down this Newton's second law for these two separate bodies. They're two completely separate bodies. We're going to use the same axes for both of them for the moment. So we're going to make this, there's our y-axis pointing up. And let's write down the sum of the forces for M1. So T points in the positive upward direction, minus M1G points downwards. Notice I'm not really using vector notation here because this is essentially a one-dimensional problem. We only have the y-axis here. So we can kind of just shortcut it and not use vectors at all for this one. So that's the sum of the forces for the first one. The sum of the forces for the second one is going to be T m2 minus m2g. Oops, sorry. Okay, but what do they equal? They equal a mass times acceleration. So the mass of 1 times the acceleration, the mass of 2 times the acceleration. Okay, now again, I've not put 1 and 2 on here. And why haven't I put 1 and 2 as the two separate accelerations? Well, this is an example of what we call kind of an assumed constraint within a mechanical system. So the constraint here is that the string doesn't get any longer. So we'll see later when we talk maybe about materials that the tension comes from stretching the material, and we've seen that in when I was talking about where tension actually comes from. Stretching the atoms apart produces the tension force. So the string kind of must really get longer, but for fairly depending on the material, that's probably a very short amount. So what does it doesn't get longer mean? It means that if as this is moving, as one is moving up and one is moving down, they must be going at the same velocity at all times. Imagine they weren't going at the same velocity. Imagine 2 was going faster than 1. If 2 was going faster than 1, then it would be going down more meters in a second than this one went up, which would mean the string would have to get longer. If the string gets longer, the tension is going to increase, which is going to accelerate this one and slow this one down. So they must go at the same speed, otherwise either the string will go slack or the string will go tighter. So if they're going at the same speed all the time, they must also have the same acceleration all the time if they start from rest. So our two accelerations are actually the same. However, they are numerically the same, but the acceleration is going to point in opposite directions. This one, I said, is heavier than this one. So this is the one that is going to go down. So I'm going to call this one A in this direction. And this one's acceleration is going to be in this direction. They're going to be opposite. So M2 is going to have a negative acceleration and M1 is going to have a positive acceleration. One important thing about positive and negative acceleration, negative acceleration does not necessarily mean slowing down. If something is moving, for instance, in the positive x direction, if it's going in this direction and it has positive velocity, so it's going in this direction, then speeding up would be a positive acceleration in this direction, and slow down would mean an acceleration in this direction, which would be negative. So in this case, negative is slowing down, positive is speeding up. But if the thing was going in the other direction, if the thing was going like this with negative velocity, then negative acceleration would mean speeding up, because it's already going negative. This is making it go more negative, and this would be slowing down. Okay, so negative acceleration does not mean slowing down. It depends on what direction the velocity is going. If the acceleration is in the opposite direction to the velocity, it's slowing down. If it's in the same direction, it's speeding up. And because these two objects are going in opposite directions, their accelerations are in opposite directions, even though they're speeding up. Okay, so we have this. What we're trying to do is find an equation for the acceleration. So we're going to solve these two equations. They're linked together by the same tension and by the same acceleration. We will look at situations later where the tensions are not the same between the two. There are situations where the tension in the two halves of the string will be different. For the moment, we'll kind of have this simple situation where they're the same. So how do we do that? Well, we can basically solve both of these for t. We don't know what t is, but we can eliminate it between the two equations. So let's rearrange equation, we'll call that equation 1, that equation 2. So equation 3 is from equation 1. I'm going to rearrange this. T is m1a plus m1g, and rearranging the other one, T is m2g minus m2a. Notice the difference in sign is still in there. So now we can set these two equal to each other to do a to kind of eliminate the t. So we can just make the right hand side of this equal the right hand side of this. So we're going to have m1a plus m1g equals m2g minus m2a. And we are going to collect together our a's maybe on the left hand side here. So we will have a, I'm going to take them out of the brackets. If you don't get the step I skipped, click the pause and see how I did that. So I've taken the a over this side. I'm going to take the g factor of the other side. That's going to become m2g minus m1g. And then you can see I can just divide through by this factor I'm going to get. And I'll take the g out on the side. We're going to have g m2 minus m1 divided by, and just to keep it looking symmetrical, I'm going to say m2 plus m1 here. Okay? So, and does this make sense? Well, if you take a look at it, you can see that if m2 equals m1, then the top of this will be 0 and it won't accelerate, which is what you'd expect. If the two are the same mass, they're balanced, one isn't going to speed up over the other. If our masses were the other way around, so if we reverse this so that m1 was bigger than m2, then this would become negative and our acceleration would be negative. So actually this equation works for both. All we have to bear in mind is what we have defined as being a positive. So we have defined a essentially as being the acceleration of m1 in the upward direction. Okay, so if that's positive, it means m1 is going up. If that's negative, it means m1 is going down. Okay, so that's fairly straightforward. A couple of things in there. So we have a constraint, which is the string, sometimes called the string constraint. It basically says that the string means that the two things are going are connected, so they have the same acceleration. As I mentioned, we'll come to situations where the tensions are actually different between them, but that isn't important right now. Okay, so again, the process was the same as for the some of the other force examples. You just start by identifying your bodies and forces. So we did that here, created two different free body diagrams, and then we wrote out Newton's second law for the two, and then we started to solve them mathematically, and we got some algebra. Notice here, again, I'm not using any numbers, I'm just doing this entirely with algebra. If we had been given masses for this, we could plug them in here and give ourselves an answer. But really, getting used to going through these algebraically saves you kind of a lot of time, and saves a lot of errors. Okay, so we could up the complexity a little notch there, and we could make this a little bit more tricky. So here we've got another two-body kind of problem where we have a pulley is now attached to a ramp. Okay, let's make that angle theta right there. And we've got, this time, M2 is sliding down the ramp. I'm going to leave off friction for a moment, but we could put it on. And M1. Okay, and we're going to again say what is the acceleration of M2, for instance. So again, what we're going to do is draw free body diagrams for the two different objects. So let's do that. So here is let's put it down here. Here is M1. And there's that tension again. And M1's weight, which is M1G. And then we would draw the free body diagram for our little block here. So here's our block. Now this one's resting on a ramp, so it's going to have a normal force which points at 90 degrees to the ramp. It's going to have the tension in the string, and we're going to assume that's kind of completely parallel to the ramp, so let's put that there. Same tension as before. Again, it's a massless string connecting the two, frictionless pulley, so we're going to have the same tension in both pieces of the rope. And now the weight of this one is going to hang down like that, M2G. So we now have two separate bodies again. They're again interacting through this tension. Now when we've done ramp problems, we've seen how it's best to align our axes along the ramp. And for this, for just vertical like this, we saw from the last problem, it's easier to align it vertically. So which way do we put our axes? Well, actually, each body can have its own set of axes. That is okay, as long as you keep track of how the things like the accelerations, etc., transform between the two. So we can, where it's perfectly okay with these two bodies, to call that the y-axis for this one, y and x, and for this to have its axes like this. Let's maybe point them down the slope, so that we can have all the benefits of the sort of simplicity of solving these with axes that line up with their accelerations. So all we have to do, though, is be clear again about what we mean by particular accelerations in each case. So we're going to assume again for the moment that M2 is bigger than 1, that it's accelerating, so M1 is going up and M2 is going down. So our acceleration here is going to be A, and it's going to be in the positive y direction. And our acceleration here is going to be in the positive, this time, x direction. In this previous problem, I gave both of them the same axes. And in that case, this was up for this and down for this were opposite signs. This time, A, again, we're treating A as a positive number. Positive A means y up for this and x down for this. So we're now going to write out our Newton's second law for these two separate bodies. Okay, so Newton's second law applies equally, separately to the two individual bodies. Okay, so let's do that. Let's do for M1 first. So M1 is nice and easy because we can kind of write it down straight away because we know the tension is entirely in the vertical direction, and so is M1. So we can just as before write T minus M1G equals M1A. And that is positive acceleration because that's the way we defined it. So for M2, it's a little more complicated. And I'm going to do it in my little table of to just kind of write down the x and y components again. So I'm going to say I've got, let's make my table, x and y components. Draw that kind of like that, of t. So if we look at this, we can see that t only has an x component. It points in the negative x direction, so we're going to have negative t and 0 for our components of t. For the normal force, we are going to have, well, this points entirely in the positive y direction, so we're going to have no x component and just a y component. And then finally the weight, I'll put W there, or W2. This one is going to have two components. It's going to have an x component, and again, theta is this angle here, so theta is also actually this angle. So in this case, it's the sine component, which is x. So we're going to have, and this is in the positive x direction. Again, I'm doing this in in a way to do, I'm kind of manually filling in the signs of the trigonometric angles. I could, if I wanted to, be really, really strict and call this my positive x-axis and measure this here as negative 90 minus theta, but it's a simpler problem. I'm going to not go into doing all that at the moment. So let's call this the x direction is our m2g. What did I just say? Sine of the angle. And the other one is m2g cosine of the angle. And you can see that the y component of this is negative. Okay, so that's negative. So these are going to then add up to acceleration. So my acceleration is in the positive x direction according to the coordinate system I've chosen for this. And so that is going to be m2a. And there's nothing in the y direction, so that's going to be 0. So I can write out my 2 Newton's second law equations for this particular second body. So I've got minus t positive m2g sine theta minus t plus m2g sine theta equals m2 times a. And then for this one I have my normal force equals negative, sorry, that doesn't equal, sorry, normal force minus m2g cosine theta adds up to 0 in this case. Okay, so yeah, we have x and y components. So we have 3 equations that are that require solving. I'll just write those out again on one sheet so that we can see them. So we have we have for the first body t minus m1g equals m1a, and then for the second body we have negative t plus m2g sine theta equals m2a, and finally we have a third equation, n minus m2g cos theta equals 0. Okay, so these are now our 3 equations, and we're trying to find acceleration. That's what we want to what we actually want to find here. So acceleration is an unknown, tension is unknown, and the normal force is unknown. But we have 3 equations, so we could find all of them. We actually don't need to find the normal force. We've not been asked to find the normal force. You can see that actually the normal force can be calculated like right away. If we know the mass and we know the angle and we know g, we can actually just calculate normal force right away, and it doesn't affect any of the others anyway. If we'd maybe had friction in our problem, then we'd have had a friction component up here as well, which would have had the normal force in, and then we might have had to worry about it. But this way we don't have to worry about it. We can actually just solve just as we did before for the tension. So let's do that. So we're going to say that t equals m1 a plus m1g, and then if we rearrange this second one here a little bit, we're going to have t equals that's mine. So it should be m2g sine theta plus, do I mean plus? No, minus m2a. Okay, again, we can set these equal to each other. We're going to say m1a plus m1g is m2g sine theta minus m2a. And then we could rearrange these, get a on its own. So again, we're going to have something very similar to what we had last time. We're going to have on the right hand side a, and on the left hand side we're going to have g, and this time it's going to be m2 sine theta minus g, sorry, minus m1g, sorry, not minus m1, divided by m1 plus m2. Okay, so similar kind of result we had last time. Last time we had this one, now we have this one, and we've got this sine theta added on to, or multiplied onto the m2 that we had before. Okay, the m2, which is the one on the slope. So similar kind of equation. What I wanted to point out there was that this is the the bodies are still connected, but they can each have their own coordinate system, which is convenient to the two bodies when they're connected, like through a tension like this. And then it can be really convenient to kind of do that, keep the math all very straightforward and simple. Okay, right, next problem. Okay, so there we looked at a couple of situations where we had pulleys, and pulleys are a really useful device, one of the oldest machines that we've invented as humans, and they allow us to manipulate forces in a way that's to our advantage. So let's look at, for example, a simple pulley like we just had, and there is a mass on the one end of the pulley, and then it goes over the other side, and you are trying to pull this thing up using the strength of your own body. Okay, so if you want this thing to go up, you need to apply a force here, which has to at least equal the tension here, and that has to, if we look how big is the tension, well, if we look on the other side, this has the same tension pulling up and mg pulling down. Now if we are going at constant velocity, suppose you want to pull this up at constant velocity, so that t minus mg equals 0, and t minus this force that you're exerting equals 0, you can see kind of straight away that the force you have to apply equals mg. Okay, so you can pull this thing up by pulling on this pulley, but you have to apply the same forces you would if you just picked this thing straight up. So it's not really giving you huge amount of advantage, other than maybe it's more convenient to pull it up like this. You can keep your back straight, it's kind of safer. However, let's make our pulley a little bit more complicated. So obviously this pulley must be attached somewhere. Maybe it's attached to the ceiling somehow. So let's make it a little more complicated. Let's take our ceiling here, and we will have a pulley like this, and we're going to attach the string to the ceiling. The string is going to come down, it's going to go around the pulley, and then it's going to come to another pulley. We're going to have a second pulley right here. Okay, and you are going to stand down here on the bottom. And again, you are going to pull on this pulley. Now this is going to be attached to the ceiling as well here, so this one is fixed. This pulley is completely hanging, and on the end of here is a little hook, and there is my mass that I'm trying to pull up. Okay, so we can kind of treat this whole thing as one particular object. So again, we're trying to pull this up by applying a force here. And in this direction, that's producing a tension. And this tension is the same all the way around the rope. So what about over here? Here we definitely have mg pulling downwards. But what do we have pulling up? Well, we have two ropes. This pulley knows nothing of what's beyond these two strings. So the pulley is actually pulled by tension on both sides of the rope, here and here. This same tension pulling up on this side of the pulley, the same tension pulling up on this side of the pulley, the tension is the same all the way along this rope. So now when we write this down, if we write down the equation for our part here, again, we're going at constant velocity, so acceleration is 0. So we're just trying to pull this thing. If we apply more force, we can make it accelerate. But if we apply at constant speed, then we're going to have, again, T minus F equals 0. Okay, so the force we apply equals the tension. For the other body here, we're going to have two tensions in the upward direction, minus mg equals 0. Well, what that means is that T equals mg divided by 2. And so our force equals mg divided by 2. Okay, so what this pulley has allowed us to do is to double up the tension in the rope, to basically half the amount of force we have to apply in order to pull this object up. And you can carry on doing that. You can put complicated arrangements of pulleys that quarter this, eighth this, make it more and more, the force smaller and smaller. So the pulley allows us to amplify our force. So if you could only just lift this weight with this setup you would be able to lift twice as much weight. So this gives us something that we call mechanical advantage, and there are lots of ways that we can get mechanical advantage using simple machines. The pulley is one. We'll look at others later. Now you might be thinking, like, that's just awesome. Why don't we just have 1,000,000 pulleys and make the the weight completely negligible? Wouldn't we be able to do anything? Wouldn't we be able to lift anything then? We'd seem to be getting force for nothing. Well, it's not for nothing, and we'll see later that there is a payoff for doing this. There is a something you have to give up in order to be able to do this. But we'll save that for later when we're talking about energy. For the moment, this is one of the main purposes of pulleys, is to give you extra force. Okay, so those have been some fairly kind of like abstract problems so far. I want to look at one slightly more applied problem using pulleys next. So this is, I'm in the way of the thing. Which way do I go? Over that way. So this is an example of something called the Russell traction system, and traction systems are used a lot for setting badly broken bones. So why do you have to do this? Well, basically your muscle and skin and connective tissue within your limbs is actually under tension most of the time. So if you break a leg, break a bone in your leg, the muscle, etc., is trying to pull the leg together. If the bones don't actually meet, then that muscle can pull them together so that they don't meet properly and they heal in unusual ways. So the way they get around this is by applying a constant force to your limb whilst the bone heals, to prevent the bone, or to keep the bone straight and healing in a clean way. There are actually lots of different setups for this. This is one particular one called the Russell traction system, but they all have pretty much the same idea. They use a system of weights and pulleys to apply a force to the leg. So in this particular one, this applies a constant force to the fractured leg while healing, and the objective is to keep the force on the leg pointing along the axis of the leg. So if the leg is lying this way horizontally, you're wearing some special boot, or maybe this is a cast, pulley attached to the cast, and we're trying to provide a force in this direction, pulling the leg. So there's tension in the leg, which means that that same force is pulling back in the opposite direction. So we want to say what is the angle and the force on the leg, or the force off the leg. Okay, so we are going to go about this in exactly the same way as we have each time. So let me just, oh, it's the wrong one. Let me, where has it gone? There we go. Let's again sort of simplify this. So we've got simple diagram first. We've got the pulley coming down, or the string coming down off pulley. We've got it coming out to the sort of foot arrangement here. We've got the a third pulley here. These two pulleys are really just redirecting the force. And then finally we have a weight on the bottom, which provides, this is basically providing the tension in the string. And then we have the foot attached like that. So, and that's really badly drawn foot, sorry. So we're going to try to apply a force in this direction. So if we're applying a force in this direction to the boot, the leg is applying the same force back. So just as before, we're going to do our free body diagrams for each of the bodies. So we identify the bodies that we're looking at. One is going to be this, the mass hanging off the end. One is going to be the leg system. So for the leg system, we're going to have, and I should draw the angles on here as well. So we've got an unknown angle here that we're going to try and calculate. And we've got then a known angle here of 15 degrees. Okay, so this is the sort of weight of the leg. So I'm going to call that L. It's not the weight of the leg; it's the weight of the kind of boot cast thing. And so we're going to have a total of 4 forces acting on this. That cast is itself going to have a weight. So its weight is going to be ml times g. There's then going to be a force pulling back on it from the leg, and this is actually the force we're trying to generate. So this is the leg pulling the cast, and because of Newton's third law, that will be the same as the force of the cast on the leg. And then we have the tension from the 2 sides of this rope, one going in this direction, unknown angle theta, and one going in this direction, 15 degrees. Okay, and again, this is the force T. Okay, so that is this body. For the other body, we're going to have, I'm going to call it the mass of the hanger, tension, and MHG here. Okay, so we have 2. Again, we're just going to go ahead and write down Newton's second law for each of these. So for this one, we're going to write down x and y components again, and I have kind of 2 tensions. I'm going to call them T1 and T2. But remember, the magnitudes of these 2 are the same. The magnitudes of these 2 are the same as the magnitude of this, but the actual vector has different components for the 3 different situations. So here, the components are going to be T in the vertical direction. I should have drawn in my axes. There's Y and X. So for T1, which is this one, T1 and T2, this is going to be T in the X direction cosine theta. and it's going to have a component in the vertical direction of t sine theta. And then t2 is going to be pointing, is going to be t cosine 15 degrees, and negative t sine 15 degrees, because you can see its points down below the x-axis. The weight of the hanger is going to have nothing in the x direction. It's going to have negative m leg g in that direction, and then finally L is going to be entirely in the negative x direction and nothing in the y direction. Okay, this is a static problem, so this is a problem where there is no movement of the object, so the sum of the forces is going to be 0 in both cases because it's not accelerating. Okay, if your leg starts accelerating in this situation, you're going to have problems. So we're going to add up the x and the y for that. We're going to have the equation t cosine theta plus t cosine 15 degrees, nothing for 0, minus L equals 0. And then in the y direction, we're going to have t sine theta negative t sine 15 degrees minus mlg equals 0. And then, so we've got these two. And if you just look at this right now, we actually have three unknowns. We have the tension, we have this force in the leg that we're trying to find, and we have this theta, this angle that we don't know. So we have three unknowns, but we do have a third equation we can create, which is the Newton's second law for this object. So that we can make y in that direction again. And so for this object, we can write t, same t again, minus mhg equals 0. Okay, so now we have three unknowns. We have three equations. We can go ahead and solve it. So, right, so if we're going to do that, we are going to kind of reorganize that. Yeah, let's see if we can actually solve those equations. So we're going to have t cosine theta plus t cosine 15 degrees minus L equals 0, t sine theta minus t sine 15 degrees minus mlg 0, and t minus mhg equals 0. Okay, so we have two pieces of data, which is that that we can get rid of the t in these ones using this equation first. So we've got t is mhg. I'm sorry if my little subscripts aren't very clear there. Hanger is the L is the hanger, L is the leg, and H is like the hanger. So we substitute that back in. We're going to have mhg cos theta plus mhg cos 15 degrees minus L equals 0. And then we have, sorry, to look at a solution, mhg sine theta minus mhg sine 15 degrees minus mlg equals 0. So, so now this has two unknowns and it has the L and the theta. It's kind of up to you how you want to, like which one you want to solve for first. But if you look at this equation only contains one of the unknowns. It only contains sine theta. It doesn't contain the L at all. So this one would be best to just work out first straight away. So what we can do is just kind of rearrange that for sine theta, which is unknown. So if we do that, we're going to get sine theta, and we are going to just put this on the other side. So we're going to, in fact, put both those terms on the other side. We're going to have ML over MH, MLG over MHG plus MLG what am I doing? No, sorry, MHG over MHG sine 15 degrees. Okay, so I've just rearranged this. So we can see that actually these G's are going to cancel here, G is going to cancel here, this MH is going to cancel. ML is 4 kilograms, this is 6 kilograms, so this kind of simplifies really nicely to 2/3 plus sine 15 degrees. If you put all that in, you're going to get 67.7 degrees. Okay, so that is, so theta equals 67.7 degrees. Okay, so we can put that back into this equation. We're going to rearrange it, and what you should find is L equals 79.1 newtons. Okay, so yeah, all of this is again just kind of solving the math of the equation. But let's just look back at what we did. We drew free body diagrams for each individual object. This time they had the same axes as each other. Again, it doesn't matter what axes you use for each body, they can have separate axis systems. We worked out our components for the forces in the more complicated one. This one is only one dimension, but it was kind of straightforward. We get 3 equations with 3 unknowns, and we can go ahead and solve them. Okay, so that was just a little thing on solving problems with strings, with tension, yeah, hopefully it should be useful. Okay, I will do another video like that on solving some problems with friction next, but for now we will leave it at that.